And I realized that number 3 was kind of fascinating. It took me quite a bit of time to set that up. And then this morning I realized I made a mistake. Now again, I mentioned to you that if you have it's all relative. And the relative numbers in the first version were correct, and I'll explain why that is. So the question is fine, it's just I updated it with the right numbers. And when I realized the mistake I made, I'm like, well, that's actually kind of cool to show how I made that mistake and why I made that mistake. There's like a lesson in it, right? So remember, I also emphasized to you, recognizing when you made a mistake is way more better. You are a more useful person to recognize mistakes than when the machine is humming along and you're just standing there, like an idiot, right? Companies hire you not so much to babysit machines, it's when the machines break. That's when you're useful. So, but before I go blah, blah, blah on that, any of you have any questions? Anything at me? So nothing? Okay, if you're sure. All right, now remember, there were people asking about homework, things not adding up. That happens. Come by office hours as normal. Okay. Now, we'll end a little early today. This isn't going to take a whole hour. This is kind of a neat question, though. So question 3 on the homework is a colligative property. And so what I was trying to do was remind you about how chemical potentials of a gas is equal to the chemical potential of a liquid. And then for water, that's true at 100 degrees C, and let's just say 1 bar. 1 bar, 1 atmosphere. Wherever they're in equilibrium, they're in equilibrium. 1 bar, 1 atmosphere. They're not quite the same, but anyway. All right, the chemical potentials are equal. Now, if you dump in some salt, okay, so if you dump in some salt, then you change the chemical potential of the liquid, you drop it a bit, and so the temperature has to adjust because it's modulating these parts. It's modulating these. Once you've dumped in, I think I say you dump in 38 grams of salt into 100 grams of water. I think that's what I did in the question. That drops the chemical potential of the liquid, so the temperature has to adjust to get them back to equilibrium. And so that's what the lecture was, and so I wanted to put some numbers to that. And to do so, what I had to do was I wanted to give you some real numbers for the chemical potentials. So I calculated those. You can't, oddly enough, you can't really Google this stuff. And I find that bizarre because I can find just about anything on Google. Okay, so let me give you some numbers. Now remember, so there's a lot of lessons into this question. So that's why I actually really kind of like this. I'm glad you stuck around. Okay, you know that the chemical potential is really the delta G of formation per mole. Right? Now, some of the book in chapter 8 describes phases in terms of just the Gibbs energy. And there's nothing wrong with that, except that I just don't know the absolute Gibbs energy. If I'm going to do this with real numbers, then I have to collapse into this basis set, that's the word I use, basis set of formation energies. Otherwise, I have no way to put real numbers down, to do actual calculations. Otherwise, it's all just pie in the sky and very hypothetical. Okay, so let's do liquid and then the gas or vapor. And now, of course, let's do 25 degrees C, and this is in the table in the book. And these are all in kilojoules. And so part of this is you have to be careful of kilojoules per mole versus like delta S times T, which would be in joules per mole, delta S per mole. Anyway, so let's see, the liquid is 273.129. And the gas is minus 228.572. And as I've said a zillion times, it is part A of question. I'm just going to give you the answer. Of course, the phase with the lowest chemical potential is favored. And obviously, water, despite all the blah, blah, blah I said a little while ago, the liquid is favored. You have liquid water at 25 degrees C and 1 bar pressure. And of course, its delta G of formation is the lowest. One way to think of that is if I ignited oxygen and hydrogen, it would generate the most entropy by forming a liquid. So that's another way of thinking of that. Okay, at 100 degrees C, now I actually was not able to find this information. I had to calculate it. And here's what I got. Minus 225.1545 kilojoules per mole. That was for the gas. What did I get for the liquid? You should know it.
Oh, same thing. It's the same number.
The what?
Same thing.
Same number. Right. I got the same number. And I'm going to show you how I calculated it. That's kind of the whole point of this. I get the same number. Because they're in equilibrium. Of course I should get the same number. Okay. Now, number 3, by the way, contains the answer to number 2. So I'm just kind of hemorrhaging my guts. So just look at that. Addition of salt means that the equilibrium point changes to 105.44. Okay. Now, here's what I got. I got minus 2. Now, this is for the pure. This is the pure liquid. I'm not drawing this very evenly, but the gas is minus 224. Okay. So, which one is favored? The gas. Of course, it has the lowest delta G. Not by much. It's kind of narrow. But then again, you're not exactly very far off the equilibrium point either. So they ought to be still kind of close. But of course, if you have water above 100 is steam. And ta-da, you magically proved that. So good going. All right, now, you know that. Now what you do in the question, and this is very easy. So that's why as much as, I had actually messed up these numbers when I posted it last time, and I fixed it this morning. It doesn't matter, I have the relative numbers correct. So what you do is you plug that number into the gas, you plug this number into the liquid, and then you figure out what mole fraction makes this work, and guess what? It ends up being the saturated solution, the saturated value, the value for saturated water, salt saturated water, which is part of question 2. So anyway, I made them, I got them to work together. Now, I want to tell you how I get these numbers. In number 2, I actually fudged this one. I fudged this one. This is not actually what I calculated. I actually calculated minus 224.309. I fudged it a bit. Now, I fudged it to make it work with question 2, so there's part of that. But I have a good reason, and I'm going to explain that. Okay, but before I do that, let's figure out how I calculate these to begin with. And I am going to mislead you horribly. Okay, so you got to remember that these are formation Gs per mole. And we're going to do this at other temperatures. Now, hopefully, you have your head together enough to know that this is I need to calculate the formation H at T2 per mole. I may forget the per mole. Minus T2 delta formation of S per mole at T2. Okay, this is correct. I haven't tried to, I'm going to try to trick you here because I tricked myself. And I'm going to do the gas. So I'll do the gas. So what I'm doing is I'm calculating the Gibbs energy of formation of gas, and I'm trying to figure that out at 100 degrees. Okay, so I look this stuff up. And what I get, and now again, this is in the book, the number for the enthalpy, you can look as well, kilojoule. I'm bad about numbers when I have a zillion of these to write. Okay, now, to change the enthalpy, if I'm going to go off temperature for enthalpy, how do I change the enthalpy?
Change the temperature.
Well, just
CP delta.
CP delta T, right? CP delta T. Okay, so that's 33.58 for gaseous water, joules per kmol. Okay, now again, be careful. I'm not gonna fix the units. You can do that on your own, or you don't have to. Yeah, it doesn't matter much. Okay, T2, that's like 100 or 105 minus 298. I'm gonna just leave off the 0.15 anyway. I'm gonna be a little loosey-goosey with this. Okay, so there's the enthalpy correction. Let me do the entropy correction, T2. Okay. The entropy of gaseous water is 188.825 joules per k mole. Oddly enough, oddly the same as the heat capacity. Those are always related. And then, now how do I fix the entropy? Entropy is going to go up. Well, what's the correction factor? CP what? Natural log. Yeah, I mean, people should remember. So CP, I'm just going to write it out. 33, it's the same number, 33.58 joules per k mole. Natural log, T2 over 298. Here, I need to make this a little bit more clear what's what. There we go. Okay, right? Okay, and this ends up being minus 312.57. And this is for, what did I do? This is for 100 degrees kilojoule per mole. This is for T2 of 100. Ta-da! Is something wrong? No, don't you remember? Sorry, I erased. That's the wrong number.
Yeah.
That's not right. Okay, now we got to start figuring out why. This is why this is a good lesson. Mistakes and figuring out why your mistakes are probably the best way to teach a class, in my opinion. And I strongly emphasize that. Okay, now, a while ago on a homework set, I had you reproduce the delta G from the delta H and the S. I said, calculate delta H minus 298 times S. And you did not get the delta G. Why not? Here, let me write that down. Now, we're doing that, no temperature dependence. What I've done is I've drawn a really complicated example, and I've done it wrong. We're going to figure out bit by bit why. Okay, delta G formation, and no temperature. Let's make it easy. Per mole. Oh, sorry. Sorry, the symbology matters, but I screwed up a lot. This is what you tried to do, but it was wrong. And then I walked you through getting it right. What was incorrect about this? No, units are fine. Joules per, well, joules, kilojoules, okay, but let's not have our head up our ass. It's we'll fix the kilojoules and joules, right? Because we have a kilojoule and joule problem here. What's wrong?
It's not a change of entropy?
Yes, it's not a change in entropy. You're supposed to have delta formation entropy. Right. Yeah, remember that this is not an absolute quantity. This is the formation of, we're doing gas water. This is the formation enthalpy, entropy, Gibbs energy for forming gaseous water from gaseous O2 and gaseous H2. So what you had to do was, oh, now I know what I'm going to put on the final, by the way. Oh, I'm going to do this right. Minus entropy per mole, H2 gas, minus 1/2 entropy per mole of O2 gas. Okay, you remember doing that? Yeah, you do. Sure. So, well, it was on a homework set. I don't remember. I got it off of my print. That's why I'm telling you not to do that. Anyway, okay. Now let me fix the let me fix what we did here. Okay, so unfortunately it gets more complicated. So I've done so it doesn't look too bad. I'm just going to be writing a little bit more, and I'm sorry to write in place of what I've already been doing, but it's it's really a bunch of numbers, so it gets a little complicated. Okay, so this is the correction for gaseous water, its entropy correction, but I have to subtract from that, the numbers for H2, and I'm using the same numbers, and I have to use their heat capacity. So these are the numbers for hydrogen, so maybe make a note. Units, I'm trying to be careful about that. Okay, so that's I'm subtracting out the entropy of, here, I'll make this more clear. I'm subtracting out the contribution from hydrogen, that's its heat capacity. Okay, then you have to do the same for water, and that's 205. And again, you can double check that these are the proper numbers in the book, especially if you feel like repeating the calculation. I use MATLAB because when I make a mistake, which obviously when I have this number of numbers, I make lots of mistakes, and MATLAB makes it easier to go back and correct it. When I do, when my finger just slips. Okay, ln T2 over 298. Okay, sorry, in bracket. There you go. All right, so now you see, yeah, you're not going to just do this on a calculator, especially when you make a mistake. And the result is minus 221.904 kilojoules per mole. Ta-da! What?
Still the wrong number.
I ain't right. Whoops. 225. Look at your notes. 225.1545. This is the wrong number. What I do? This is the number I put in the homework yesterday. And I realized I made a mistake today. And I fixed it today. So that's what we're doing right now. What did I do wrong? This was a big one. You gotta admit, that's a big mistake. It's a reaction. Now here's a hint. The fact that these are formations, which are reactions, appears twice. I've made one correction, where's the other one? Hint, heat capacity. Kirchhoff's law. Where's the error? I've just fixed entropy. Heat capacity of water, heat capacity of hydrogen, heat capacity of oxygen. I can always tell because oxygen gets the half. Where did I make a mistake? Because this isn't the enthalpy of a chemical, it's the enthalpy of a reaction. Okay, let me point out that for a reaction, let's do a reaction. Let's do a temperature dependence. Let's do temperature dependence of enthalpy. Right. So no little knot anymore. Okay, where's my mistake? Where?
Again, you did the heat capacity for the pure thing instead of the change in the heat capacity.
Exactly, right here. Now you see that? That's the heat capacity of steam, and I need to subtract from that the heat capacity of hydrogen and 1/2 that of oxygen. Right? Okay. Now look that up. I'm not going to, well here. Delta CP 33.58. So, right, I forgot to subtract out those numbers. 28.64 minus a half. So yeah, you see I'm using the same numbers. Where am I at? Where am I? Sorry, I'm lost. 29.4, yeah, 20. So that's what I need to have up here. Right? Okay, what about here? Sheet capacity right here, right?
Oh, it's fine.
Huh?
That should stay the same, no? The bottom one?
Well, I mean, I have heat capacities. I need to put that here too, right? Yeah, shouldn't they all be delta CP? Right? What do you think? Who votes? All of these should be delta CP. 1, 2, and who thinks these should stay the same? Same 3 people. Never had anything like that happen. What do you think though? Seriously, somebody except the 2 people who voted twice. What do you think? No? So it should stay the same? Anybody else?
Here's what I'm thinking. I'm thinking since that top term takes into, that one. That's already the change for the reaction, so
that's for the enthalpy of the reaction. These are entropies. You want to disconnect the two.
Okay.
Right. Remember, one's like, this sends entropy outside, and this is the entropy of the inside. Right. And the total is delta G times minus T.
Okay. So I see the big.
So these are kind of disconnected. So outside entropy change, inside entropy change. Entropy is all that matters. So you want it. So again, delta CP or CP.
Delta CP.
Okay, delta CPs. If we did delta CPs, we would get minus 226.3809, which is wrong. It's wrong.
It's CP because the allied term already takes care of the change in temperature.
Well, yeah, that's the change in temperature. It's just what heat capacity you use. The answer is that you actually don't change this. This is correct because what you're doing is you're changing the entropy of. Remember that the data tables have delta formation G, delta formation H, S. S is different. It gets treated different at all steps. So what you're doing is, remember that this whole thing is technically your delta reaction. Whatever part of this is a reaction, the whole thing takes care of that. So that means that the heat capacities are for the individual species. So that is correct. And if you do this, then you get the right value of minus 225.154. Okay, now this is how I got for the gas. But when I got the liquid, now let me write this up again. When I got for the liquid, and we're almost done, just 5 more minutes. So we'll get out a little early. Unless you want, I'll stick around in case you have any questions or something. That's fine. Okay, so now let's do at T equals 105.44 K. Delta formation G per mole at that temperature of the liquid. In the homework, I gave this value, 224.232. In the gas, I got minus 224.90. Okay, that is what's in the homework. Now the problem is it doesn't fit question 2. Question 2 is what's the change in temperature upon addition of salt, and then if you plug these into the freezing point depression question, the chemical potential modulated by the mole fraction it's not quite right. And so, sorry, it is right. Sorry, first time I'm doing this lecture. This is what I got from here. This is not what I got from here. This number, I made this number up. I made this number up so that, this is what's in the homework. I made it up so that it would fit with number 2. So that you get the right mole fraction of water to get the right freezing, to get the right boiling point elevation of 5.44 degrees. The number I actually got from this calculation was minus 224.309 kilojoules per mole. Now, when I plugged this number into that boiling point elevation calculation, it was almost consistent with the previous question. It almost gives you the right mole fraction of salt or water. It's almost correct, but a little bit off. So I made this adjustment because I wanted to give you a problem set that like everything worked perfectly. But more than that, I actually have a very good justification. You see, I know that I miscalculated this one still. I know that this one, you're not going to know this one by the way. I know that this number was really freaking solid. I know that this one could be problematic. And so what I did was, that this one could be problematic. So what I did was, I knew what the delta energy needed to be, and I just subtracted it off of here to get this number to make the questions all fit together. But now, fine and good, but here's the thing. Why am I so confident about this one, not confident about this one, to the point where I even just artificially changed the number for the questions? Yes, I did it to make them work, but I know that this number is suspect. I know that this guy isn't quite right. And I wasn't surprised when the two together didn't quite equal the previous question. That number 3 didn't quite match with number 2. So I was comfortable changing this. The reason is not just because it didn't fit with the previous question. What did I ignore? I've done a lot of temperature dependence. I changed the temperature dependence of, I changed the temperature of H. I changed the entropy temperatures. But then I assumed that one species did not have a temperature dependence. I used a number in here which is temperature dependent, but I ignored it. Which number? CP, right? This is the only thing left. I ignored the temperature dependence of the heat capacities. And that introduces that difference. Now I also told you I knew that the gas heat capacity the number was okay, and I knew that the water had to be problematic. Here's how I knew that. Let's do heat capacity versus temperature of the vapor. That is 33.46. Okay, so 33.46 and no, sorry, 33.02, and it goes up to 33.46. No, sorry, God, sorry. 02. When you go from 25 to 100. Right, yeah, this is the vapor. Now let's do the same thing for the liquid. And that goes from 75 to 76. From 25 to 100. So you see, yeah, you see this one changes by 0.04, and this is double. Right, so what I did was, I remembered that the temperature dependence, that there's temperature dependence to the heat capacity, and that for the vapor, it's rather small, but it's twice as bad for the liquid. So I knew that if I made a mistake with these two numbers, I had made a mistake with the liquid. Because its temperature dependence to the heat capacity it's way more sensitive to temperature. Question?
Why is it for the vapor phase, the CP decreasing as they go less?
Because I made a mistake. God, what is wrong with me? 33.46, 34.02. Sorry, I don't know what's wrong with me today. Just anyway, 0.06. So yeah, anyway, it's not hideously different, but it is, it is greater for the liquid than the gas. So yeah, sorry about that. And as for why the liquid is more sensitive than the gas, I'm not too sure. I just know it is. There's some levels of stuff temperature dependence and temperature dependence and temperature dependence. At that point, I hit my knowledge wall. But anyway, so I just wanted to point out that you actually can't always ignore the temperature dependence to heat capacity. And I knew that the liquid tends to be more sensitive to the vapor. So when I was designing the question, I assumed that this one was okay and that this one wasn't. And so I inserted I made the difference a little bit artificial to account for that. Because to be honest, I wasn't about to try to integrate this thing as a function of temperature for heat capacity, because then that would take me literally all day. And I know because I actually did that once. On Chapter 8, have any of you looked at Chapter 8 yet? In Chapter 8, I actually recreate the water phase diagram by doing this calculation, equal chemical potentials. And I found that not only did I have to do this calculation for solid, liquid, and gas, I had to include the temperature and pressure dependence to heat capacity. And if I didn't do that, it was completely off. It was like hideously off unless I included both temperature and pressure dependence to heat capacity. And the thing is that I know these differences aren't too big, but when you go to higher temperatures and pressures, they start to change a hell of a lot. In fact, if you look at the figure in Chapter 8, so if you are read Chapter 8, you may notice that for the vapor liquid, I only go to 6 bar pressure, 6 atmospheres. And on the solid liquid, I went to 2,000 atmospheres. It was because I couldn't find the heat capacity, the pressure dependent to the heat capacity of those species beyond that data, and then after that, and I couldn't calculate it as a result. So anyway, well, look, like I say, I thought we could end a little early today. So anyway, there you go. I hope that incorporates a lot of lessons, and I hope that was useful to you. But that is how I designed the question.
Is that delta G information equation the same as delta G R information? Sorry. Is that equation the same as delta G R?
Yeah. Remember, formation is just a type of reaction.
Okay.